Hi, my name is Dan Clark. I'm a junior in computer engineering, and the project I was working on this summer is a camera positioning system for a semi-autonomous roundabout project, working in the lab of Professor Domitilla Del Vecchio. This project involves testing of collision avoidance algorithms on autonomous and partially autonomous systems. We have in the lab a series of roundabouts set up on a plywood test bed. We test these algorithms on small electric cars. The goal of the project is to implement various collision-free systems that can actually adapt to the presence of human drivers. And perhaps one day we'll see algorithms like this actually used in real cars and in real intersections. My work on this project is actually a little bit more behind the scenes. For these algorithms to work, the cars need to know their positions and also the positions of the other cars. And formally, to achieve this, we'd used an ultrasound-based positioning system. There were these small ultrasound units mounted on the cars, and also similar units mounted on the ceiling, and the cars would use these to triangulate their positions. But among other things, the system gave noisy data and didn't work well near walls, and ultimately the decision was made to switch to an to a camera-based positioning system. And that was what I was working on this summer, along with another undergraduate, Chao Yun. This system needed to be able to distinguish between 6 different cars, even when in close proximity. Needed to be able to track cars with an accuracy of about 5 centimeters and follow them when moving up to speeds of around 2 meters per second. Needed to be a fairly low latency system because position data isn't very good if it's old, and also needed to be a very reliable system. We run some fairly long demos, and any failure of the system for even a few seconds is enough to completely ruin the demo. So the system is based on 4 fly capture NV cameras from a company called Point Grey. They have a fairly high frame rate. This decision was made because this program needs to iterate at a fairly high speed, so very current data can be given, and also so that we can track vehicles moving at fairly high speeds. The final version of the program actually iterates at about 50 frames per second. The catch of these cameras is that they're actually black and white, so that we can't track by doing something simple like just tying a blue ribbon on the cars or something. We actually ultimately ended up using these various tracking patterns, and the way we do the tracking is by taking images of each pattern and then using these images, comparing them to the frames taken in by the cameras, and thus doing a pixel by pixel analysis and actually following the images this way. And each car actually has its own unique pattern, and this allows us not only to distinguish the patterns from the background, but also to distinguish the cars from each other so that even when they're in close proximity, there's no mix-ups. And one of the things that you'll first notice about these patterns is they're circular, and this allows us to completely bypass the problem of orientation. Since the targets look the same from all directions, there's no issues with the camera system not knowing whether the targets look the same pointing in different directions. We ran into a couple different problems, many different problems. One of them was with camera distortion. The effect of the lens on these type of cameras is that it actually can bend the image around the side, and especially in the corners. And this can make tracking difficult there because our circular patterns actually end up looking more like ovals. The way we solve this is by dividing the image up into a series of sections. And instead of just taking one image for each pattern, we actually take a series of images, one in each section. And then when an image moves into a corner section or something, we can actually compare that image taken in the frame of the camera with the image taken beforehand in that corner, so that the image we're comparing against is actually already distorted, so that the camera system can account for that, and tracking is not a problem. Of course, ultimately, we actually need to give these positions to the cars. When giving these cars positions just in pixels doesn't do them much good, so we have to create some kind of a translation to real-world coordinates. The way we do this is taking images beforehand of a checkerboard pattern and running these images through a program that can actually calculate intrinsic and extrinsic parameters of each camera. And we can then use these parameters for each camera to create a mapping between pixel positions and a global coordinate frame, which we can then deliver to the cars. And this program is actually finished now. The system is set up, and we're now using it to actually use it in different collision avoidance demos. Some things we're looking at doing this summer are a collision avoidance demo with 3 cars running simultaneously in a series of roundabouts, and also a system with 1 car that's autonomous and another car that's human-driven. And even if the human goes crazy and tries to cause collisions, the autonomous car should try to avoid it. And hopefully with this system being implemented, we should be able to create these systems collision-free. And just to conclude, I'd like to say that my experience in the SURE program this summer has been really excellent. I've learned a great deal and about the research process and about what graduate school might be like. And I would highly recommend this program to anyone considering graduate school. And that's all. Thank you for watching.